Hello everyone, I am Mr. Sunil Kumar from the Department of Mechanical Engineering, KJIT Mangalore. Dear students, I am teaching you the course of Finite Element Analysis. In this regard, we were dealing with the contents of Module 3. As you know, Module 3 contains the analysis of beams and analysis of shafts, that is torsion. Until now, we have studied about the shape function of beam, that is Hermite shape function. We have studied about the stiffness matrix of beams. So in this class we will learn about how to solve the problems in beams. There are variety of problems based on the types of loads and moments applied and the types of beam structures with respect to degrees of freedom or boundary conditions. Now we will move on to the first case. This is the beam, 1D beam with one element subjected to UDL and a point load. Okay, this is the question given. A cantilever beam is given which is fixed at one end. It is subjected to UDL throughout the length. At the same time, it is subjected to a point load, that is concentrated load, at the end of the beam. Now, the basic requirements that are required to solve the beam problem is the Young's modulus E, that is the elastic constant, and the area moment of inertia I. These are the two basic constants. Now we will continue to solve the problem. As usual, the first step to solve the problem using a stiffness method is to write the finite element model. Like the bars, beam elements are also 1D elements. So it is important to take how many elements that we have to consider. It is very important to know that how many elements we have to consider for this given beam problem. So this is a uniform cross section beam. There is no obstruction in the cross section anywhere over the length. And at the same time, there is no extra point load applied anywhere at the length. There is no change in geometry of the material. There is no extra load acting. There is no change in material itself. So in that case, the entire beam can be considered as only one element. So that is what taken here in the first step, FEA model. It is considered as 1D element having only one element. Like bars, it is having node 1 and node 2, but one thing is unlike. In beams, at each node, the degrees of freedom is 2. At each node, degrees of freedom is 2. So it is having 2 nodes, therefore degrees of freedom is 4 per element. So the size of the stiffness matrix will be 4 cross 4. So what are those degrees of freedom? We know we have 6 degrees of freedom, Tx, Ty, Tz, translation in x, y, z directions, Rx, Ry, Rz, that is rotation about x, y, z directions. Okay, now at each node there will be 6 degrees of freedom, 2 degrees of freedom. One is Ty, Ty means deflection in y direction, that is given by V1. The other one is rotation about z direction. The other one is rotation about z direction, that is given by theta 1. So there are 2 degrees of freedom. One is deflection about in y direction and rotation about z direction. One is rotation about z direction, deflection in y direction. So at each node there will be 2 degrees of freedom. So now we will move on to the next step. The next step is to write the elemental stiffness matrix. Elemental stiffness matrix for each element. Then we have to add those stiffnesses to form one global stiffness matrix. Here, since there is only one element, there will be only one stiffness matrix. So elemental stiffness matrix itself will be global stiffness matrix. Now, what is the equation for stiffness matrix? It is EI by LE cube. E into I is area moment of inertia, which is given. Le cube, length of the element, 12 6 Le minus 12 6 Le, 12 6 Le minus 12 6 Le. You can observe here the first row and the first column are similar. Similarly, third row is same as first row but opposite in sign, and third column is same as first column, opposite in sign. If you write 4L square here, diagonally 4L square here, 2L square, 2L square. Le is the length of the element. Now we have to calculate 6Le, 4L square, 2L square. We have to substitute I into E and the L value. The important thing that we have to note here is, for all the beam problems, if you can observe, the UDL is given in kilonewton per meter, length is given in meter. We shall retain meter as the unit for dimension, that is meter as the unit for length. So Young's modulus unit we can maintain as Newton per meter square. Load let us written in Newton itself. Load let us written in Newton itself, but we shall change from millimeter to meter here. So Young's modulus is Newton per meter square, 7 into 10 power 9 Newton per meter square, written as it is. I is given in meter to the power of 4, written as it is. So all the beam problems we shall maintain meter as the unit for the length. Okay, if we consider meters, we are directly writing 4Q. Here E is considered in Newton per meter square, I is considered in meter to the power of 4. Then we have to retain something outside, and inside we shall write as it is. We shall not make any corrections because there is only one element, there is no problem at all. Now this is about the stiffness matrix. Global stiffness matrix is same as that of elemental stiffness matrix since there is only one element. The next thing to write is the load vector. Displacement vector. Displacement vector Q is given as V1 theta 1 at node 1, V2 theta 2 at node 2. So since 4 degrees of freedom, we will write V1 theta 1 and V2 theta 2. Now load vector should be considered separately for UDL and separately for point load. The load vector for UDL we can write like this. UDL, it will be different for UDL, it will be different for UVL. So the load vector for UDL, uniformly distributed load, is given as P0 LA by 2, P0 LA square by the load vector for UDL is given as P0 LA by 2, P0 LA square by 12, P0 LA by 2 minus P0 LA square by 12. This is the standard equation for UDL, where P0 is UDL, LA is length up to which UDL is applied, and T is the UDL load vector. Now in the given problem, UDL is 10 kilonewton per meter. In the given problem, UDL is 10 kilonewton per meter. It is applied downwards. It is applied downwards means it is going to tend the beam to deflect downwards. That is why we will take negative. This vertical load, concentrated load also will take negative because it is going to bend the beam downwards. So the value of UDL will be minus 10 kilonewton per meter. Length of the element up to which UDL is applied is 4 meter. So The UDL load vector will be after calculation, after substituting these values, minus 10 into 10 power 3 we have to maintain, because we are applying, we are taking Newton, load in Newton. So it will be minus 20, minus 13.33, minus 20 and 13.33 will be the load vector for UDL. Now, this minus 20 is for first degree of freedom, that is V1. This is for, say, the second one is for theta 1. This is for V2. This is for theta 2. Okay. Deflection at node 1, rotation at node 1. The third one is deflection at node 2. The fourth one is rotation at node 2. Now, we have to add point load to that given UDL. See, so the total load vector will be like this. So point load is applied at node 2. Point load is applied at node 2. That point load is going to deflect the beam. So it is added with V2. The point load is added with V2. Is added with V2. So that is minus 100. So the total load vector at the third position, at the third row, will be minus 120. Minus 120. So since node 2 is applied with point load, V2 is added with minus 100, minus because it is acting downwards. So the total load will at the point 3, that is at the node 2 for V2 in the third row will be minus 120. Minus 120. So the load vector reduces to like this. So as usual, the next step will be application of equilibrium. KQ is equal to F. We have K, Q as this one, this as F. This is not equal to, this is for degrees of freedom. Now, node 1 is fixed. Node 1 is fixed means node 1 is having degrees of freedom 1 and 2. Therefore, entire first column is eliminated by elimination method of boundary condition. Entire first row and second row is eliminated. At the same time, first column and second column is eliminated. Remaining terms is written here. This 12 minus 24 minus 24 64. It's a mistake here. So this 12, this term, this term, this term and this term are retained. 12 minus 24 minus 24 64. V2 theta 2, because V1 theta 1 are arrested because it is fixed, into minus 120, 13.33 is kept. After calculation we get V2 as 0.8762, that is meter, deflection in meter. Theta 2 will get as 0.3238. That unit is radians, that is the rotation in clockwise direction. That is why the value obtained is minus, however it shows clockwise. Since it is deflecting downwards, it shows negative. So the overall nodal displacement vector, we can write it as 0, 0, minus 0.8762, minus 0.3238. This is the final answer. Hope you have understood the first problem. We shall move on to the second problem. This is the 1D beam with roller support under 2-element idealization. Value of Young's modulus is given in kilonewton per meter square. We have to take it in Newton per meter square. Area moment of inertia is given in meter to the power of 4. Let us take it in meter to the power of 4 itself. So a beam is given here. it is fixed at one end. It's a cantilever beam fixed at one end. It is having roller support at the free end, subjected to the point load, concentrated load at the center. Since point load is applied here, we have to consider element 1 and element 2. We have to consider it as two element beam. Now, node 1 is fixed means degree of freedom V1 and theta 1, that is deflection and rotation, both are arrested. Here there will be both V1 and theta, V2 and theta 2. Here this will be node 3 where V3 is arrested. Since roller support is given, there will be no deflection downwards, but there will be theta 3 will be there, which means there will be rotation. So, which are the degrees of freedom arrested means V1 theta 1 and V3, 3 are arrested. So, as I told, FE model contains two elements, element 1 and element 2. So, at each node there will be 2 degrees of freedom. So, 3 nodes are there. So, first element is having 4 degrees of freedom. Second element is having 4 degrees of freedom. So when we combine, totally the stiffness matrix, the global stiffness matrix will have 6 degrees of freedom. Means at node 1 2 degrees, at node 2 2 degrees, at node 3 2 degrees. Totally 6 degrees of freedom for the global. As usual, the elemental stiffness matrix we have to solve for each element. For the first element, the general equation is given as EI by LE cube, and this is the equation which I have told you earlier. If we substitute the values, we will get K1 as like this. We have to take, Young's modulus we have to take in Newton per meter square, and I we have to take in meter to the power of 4. So after considering, we will reduce to K1 as like this, and K2 will be equal to K1 because both the elements is having same value of E, same value of I, same value of L. Since E, I, L are same, no need to calculate again and again. K1 will be equal to K2. So coming to the global stiffness matrix, so for the first element the degrees of freedom will be 1, 2, 3, 4. For the second element it will be 3, 4, 5, 6. So totally the degrees of freedom for the global stiffness matrix will be 1, 2, 3, 4, 5, 6. So 6 rows, 6 columns will be the size of the global stiffness matrix. Now, the addition of stiffness matrix is similar as that of bar which you have learnt until now. So the first 4 belongs to the first element, the second 4 belongs to the second element, this term, this term, this term and this term are added. 100 is added with 100, it becomes 200, 12 is added with 12, it becomes 24. That is the global stiffness matrix. There is no UDL. Since there is no UDL, no need to calculate the separate load vector for UDL. Now this is the global displacement vector. As I told, there are 6 degrees of freedom. That is why there will be V1 theta 1, V2 theta 2, V3 and theta 3. So now coming to the load vector, we can write the global load vector directly because there is no UDL or UVL. At node 1 there is no load vertically, there is no moment applied, that is 0. At node 2, vertical load is applied downwards 10 kilonewton 10 kilonewton, you can maintain kilonewton or newton, whatever it is. Here in this problem 10 kilonewton is maintained. Okay, no need to worry about that. So you have to maintain same unit throughout. So only minus 10 is written. So after substituting in equilibrium equation, this will be the equilibrium equation form. And since node 1 is fixed, eliminate first row, eliminate second row, and first column, second column. Node 3, deflection is arrested, means fifth row we have to delete and fifth column we have to delete. Remaining term for V2, theta 2 and theta 3 should be written as it is. After solving all the three equations, we will get the answers like this. This is V2. This is, the second one is theta 2 and the third one is theta 3. V2 will be in meters. This will be in radians, theta. So if minus is there, it means clockwise rotation. Plus is there, it is counterclockwise rotation. This minus represents deflection downwards. Hope you have understood. In the earlier problem, everywhere load is maintained in kilonewton. Make a note of it. Everywhere load is maintained in kilonewton. Young's modulus is also maintained in kilonewton. You can maintain in newton or kilonewton.